Welcome back to ECE 442-542. I'm entitling this short video, I hope, Quiz 3 Attempt 2 Preparation. Hopefully we can get through this quickly. Hopefully everyone is doing well, and hold on, I'm going to try to go through this. The way that I've structured this, in fact, is based on the lowest scoring quiz question in quiz number 3, attempt 1. I went from there, and then I just subsequently went to higher and higher scoring questions, but I didn't get through all of them. Everybody scored pretty well on about half of the questions, so I'm reviewing half of the quiz type questions, and they were not organized, so I'm trying to entitle them particular ways. For example, the one that tripped a lot of people up, I'm entitling Inverse Z Transform for a Non-Causal Sequence. Let's suppose then that x of n is non-causal, and you could say, for example, x of n looks like r raised to the n u of minus n minus 1. That's now saying that x of n is defined for negative indices. And suppose somebody gives you this z transform expression, z over z minus 1/4. In this case, capital R is 1/4. What is the sequence expression, little x of n? And if you look at the tables, I always seem to have an issue with this coming back after going to the camera. So now if we look at the tables, in fact, those tables are all created, most of them, the ones that you have access to from the website. Exam number 1's table is for causal sequences for k. K is consistent with our little n. K equals 0, 1, 2. These transform pairs are relative to causal sequences of time. And likewise, if we looked at the exam number 2 table, we're assuming that our sequence is 0 for k less than 0, or we're really looking at causal sequences. That's what's in this column. And so when we start looking at inverse Z transforms for non-causal sequences, we basically need to do a sign reversal, and that's talked about in some of the earlier lectures. But let's go through this example, and hopefully by the end of this preparation, you'll understand what I'm trying to communicate. From the table, if we went back to the first exam's Z transform table, we could say, oh, we're looking for, was it Z minus 1/4? So that this is in fact e to the minus at to the k, and again, k is our n. So this e to the minus at is really the 1/4, and that's now 1/4. Let me just go ahead and use our n. I can't write a k to save my soul. So here is 1/4 to the n, and this is for causal, so this is now u of n. That now from the table says, oh, the region of convergence, Z is outside of our largest magnitude pole, and that's causal. What happens when we have a non-causal? Well, with a non-causal, in fact, we have this sign reversal between our time sequence and our transform. So if we had a non-causal time sequence scaled by a factor of -1, it will actually produce exactly the same Z transform, except now its region of convergence is different. Now the values of Z that allow this transform expression to be valid, or for our series expansion to be bounded, requires that the Z values are all interior to 1/4. So when you're looking at a non-causal sequence, r raised to the n, u of -n-1, or that's equivalent to r raised to the n for n less than 0, that's another way of saying that. If somebody gave you, let's say, a non-inverted x of n, then you would have to do this sign reversal in the transform expression. Capital X of Z would then be minus Z over Z minus R. And if you want to see where does this capital X of Z come from based on this little x of n for a non-causal, go back to the end of lecture 3.1, page 12 in particular on the notes, and lecture 3.2, page 5. And lecture 3.2 tries to distinguish or justify the reasons for needing the region of convergence. You can see, I hope, that if somebody simply gave you this or that without providing you with a region of convergence, you would not be able to get back to the appropriate time sequence expression. The causal would not have a sign change in going from frequency domain to time domain. The non-causal would. I want that to be clear, and I'm thinking the reason a lot of people did miss this problem is because they went to the table and they didn't remember, maybe it wasn't made clear, but these tables all are for causal sequences, and so take that into consideration if you're now dealing with non-causal. For non-causal, you are going to need a sign reversal between your time sequence and the frequency domain transform expression. A second problem that was missed, not quite as much, but it did still deal with inverse Z transforms, and that was for complex poles. Suppose you're given this capital Y of Z expression, you would probably immediately factor or find the roots of that quadratic, and in this case they are complex, and they in fact have the same magnitude for their real component and their imaginary component. And if you were to think of this in terms of the z-plane, you would now see that those poles are at a distance 0.35 into the right half z-plane, and they are up and down in the imaginary direction the same distance in the first quadrant and in the fourth quadrant. So their theta sub d is 45 degrees, and their radius is now the square root of the real part squared plus the imaginary part squared, or in this case, since they are equal, the r would be 0.3535 square root of 2. Well, whenever you see poles, denominators that have complex roots, you can immediately say, oh, I am dealing with exponentially damped sines and I'm dealing with exponentially damped cosine. Well, which one? Well, in general, it's a combination of both. You have both an exponentially damped sine and an exponentially damped cosine. Let's look at the the two parts separately. Here's the cosine. The time domain expression, here I'm representing it as r. The poles are at a distance r from the origin and an angle theta sub d. For the cosine, you have a 0 at the same real distance into the z-plane, but there's no imaginary component, obviously, to that 0. But it's right in line with the two complex conjugate pole locations. That's the pole 0 pattern for a cosine. So if you now know the real component of your roots, you can now say, oh, do I have a 0 and is it directly underneath the pole? Then you know you have a pure cosine that's exponentially damped. You have an exponentially damped cosine. Contrast that with the sine expression. Here is the time domain sequence and its corresponding z-transform expression. Now look what we have. Now we do not have a linear term in the numerator, or I'm sorry, a constant term, and our 0 is at the origin. And what did we have in this particular example? In this particular example, if we were to actually factor that numerator, that 0 is on the opposite side of the imaginary axis. It's now with a negative part. So with our example, we actually, I don't know if I want to say that or not or show that, but here in this particular example, our pole 0 pattern, we had poles here. Now with those we go, oh, we have exponentially damped sines and cosines. Do we have a 0 here? Or do we have a 0 at the origin? Not having any luck with my stylus right now. Or in this case, we actually have our 0 right over there. The same distance into the left half of the z-plane as our poles are into the right half plane of our z-plane. And that's neither the cosine or the sine, so it's a combination of sine and cosine. Or if you found the partial fraction expansion using complex partial fraction coefficients of k1 at an angle, a magnitude k1 at an angle k1, and its conjugate, you might have originally or immediately written down the time domain expression for little x of n as 2 times the magnitude of k1, r to the n. R is the distance away from the origin. Cosine of theta sub d. Theta sub d is the angle plus the angle of that k sub 1, and that's in the partial fraction expansion of these complex poles. Well, using the sum of angles of a cosine, cosine of a plus b, you can show that in fact that is equivalent to a linear combination of exponentially damped cosine and exponentially damped sine. Here are the exponential damped cosine, here's the exponential damped sine, and they are simply weighted by some coefficient, because cosine of an angle is just a number, the magnitude of k1 is a number, and 2 is a number. So in fact, you could rewrite that as a1, some constant, r to the n cosine of theta sub d, plus a2, r to the n sine of theta sub dn, which means that this expression is equivalent to that expression. And so if you're saying, wait a minute, I didn't see this as an answer, well, you know now that, oh, he has a sine and a cosine exponentially damped, that can be made equivalent by the appropriate choice of A1 and A2 to what I ended up with. So in fact, if the structure is being asked for, oh, that's the answer. What was another problem that presented some challenges? That was the given an input and a system, what's the output? And in this quiz, I think I asked for the output structure, but in general, I could ask for the exact output y of n, or an explicit or a closed form expression for y of n. And the system could be given as a state space system, it could be given as a block diagram, an all delay block diagram, or it could be given as a transfer function. You need to be prepared for any of those scenarios. Suppose that it's given as this block diagram, and you are asked now for the structure of y of n. You need to be told what r of n looks like, so you'll have to know what is r of n, and it will have some structure. It might be exponential, it might be an exponentially damped sine or cosine. If it is an exponentially damped cosine, exciting a system in general will put some phase shift or some time delay between the input and the output, so you will have sine component and cosine component of that exponentially damped input. So if you started with an exponentially damped cosine, you're going to have an exponentially damped cosine and an exponentially damped sine, both in the output. Here, we're looking for the structure of y of n. Let's just assume we know what r of n is. That might be, let's say, 1/2 to the n. Now we know that that's going to be a piece in the structure of y of n, but what's the structure of y of n that is associated with this system and its dynamics? Well, we can determine that if we now simply label or find a state space representation, and we can do that by labeling the outputs of our delay blocks as state variable components. Here we have 2 unit delays. We will label those from right to left as x sub 1 of n and x sub 2 of n, and I'm giving generic coefficients between all of these different signal paths and the summing junctions. Hopefully you can now see that what we want to find our state space representation is what is x sub 1 of n plus 1 and what is x sub 2 of n plus 1, written in terms of r of n at the present time and x sub 1 of n at the present time and x sub 2 of n at the present time. X sub 1 of n plus 1, I hope you can see that that's d times x sub 2, it's a times x sub 1, and it's f times r. So in this case, what did I just say? It was a times x sub 1 of n plus d times x sub 2 of n plus f r of n. Similarly, we can now say, oh, x sub 2 of n is going to become b times x sub 2 of n, c times x sub 1 of n, plus e times r of n. I then said that that was b times x sub 2 of n, c times x sub 1 of n, and e times r of n. I now have my state space representations system dynamics, the phi and the gamma. What's my output? The way that I have interconnected this, my output y is simply x1 of n. And so this is my output matrix. And the structure, due to the system, I don't need to find the transfer function. I can work simply with the eigenvalues of phi, which with no feedback explicitly between my state variables, then I can just look at the phi matrix and find its eigenvalues. The eigenvalues of phi are the determinant of this 2 by 2 matrix, lambda I minus phi. That's the product of the diagonal terms minus the product of the off diagonal. That gives us then this quadratic equation. We can find the roots, and if those roots are real, then we know the structure due to the system. Again, you would have to add in or combine with that the structure of the input, little r of n. If they are real and equal, now we actually see that we have a n weighting the r sub 3 to the n, and we'll talk a little bit more about that in a subsequent example. But now we have repeated real roots, and that gives rise to this n r to the n factor, and if they are complex, then we have this exponentially damped sign that could be phase shifted. That's the theta, or it could be represented as an exponentially damped cosine and an exponentially damped sine, all with the same argument, theta sub dn. Another question was, what is this specific output sequence value, y of 2? And if it's a low index, and low here is open to interpretation, but you could think of that as being, let's say, something less than 6, maybe it's less than 3, you consider low. Here it's 2, and what can we say with this region of convergence? What do we know about our particular y in the time domain? This particular sequence says that we have a causal sequence, and one thing that somebody says, well, what were the initial conditions? So I said none of the above, and that's a reasonable response. I was assuming the system was unenergized, so in the second attempt, please assume that the system itself is unenergized or you have no initial conditions. If that's the case, then we could actually perform some long division, dividing 2z minus 1, the numerator, by the denominator, which if you multiply this denominator out, you end up with z squared minus 1.5z plus 0.75 squared. Then you could continue, but actually we've gone far enough because this coefficient in the result of that division, that actually corresponds to y at time 1. If you look at the series expansion of the z transform of capital Y of z, that coefficient would correspond to y at time 1. This coefficient that's weighted by z to the minus 2, remember z to the minus 1 is 1 delay, z to the minus 2 is 2 delays, and in this case you actually had the same numerical value for y of 1 and y of 2. In general, that is not the case. But that's then how you could quickly, instead of having to inverse z transform this capital Y of z expression, which you might need to do if it wasn't a low index expression. Another question, and this is the repeated root question. It's dealing with a causal structure, but now I think what caused people to get confused is the fact that we now have a repeated root at 1/2. So let's now see what happens when we inverse z transform a transform expression that has a repeated root. It's just like we did in Laplace domain. We simply look at that factor and we just keep including more partial fraction expansion terms until we've made our way up to a partial fraction expansion term that includes that repeated factor with the power, the highest power that existed. In this case, we have a1 over z minus 1/2. Again, we are partial fraction expanding on x of z over z so that we can ensure then that when we obtain or look for the inverse z transform of capital X of z, we will be guaranteed of having a z in the numerator. And that's what's typically there in our transform tables. If we look at the transform tables, we have a z there, we have a z there, we have a z there. We're always seeming to have this z in the transform expression, and that's why we are forcing that to be there by partial fraction expanding x of z over z. We can find a2 by the cover-up method, but we can't find a1 by the cover-up method because we would just obtain infinity equal infinity, and that's not going to work. I just used z equal to 0 and ended up with a1 being 1. So now I have, for this partial fraction expansion, a1 is 1, and a sub 2 was it was 1/4. But if you look at the tables, you will see that this is not in the table. What is in the table is your root times z. Here's your root over z minus 1/2 squared. Meaning you need to now force this term to look more like what your table would provide. So now we want to rewrite a2 in terms of b2 times the pole location, which in this case is 1/2. So if we now know that a2 is equal to 1/2 b2, b2 is 2 times a2, and a2 is 1/4, so b2 is 1/2. Then writing it to preserve that structure, which we know is in the table, now we can immediately go back into the time domain, and we know it's causal, so this is now true for n greater than or equal to 0, or we could have multiplied all of that by u of n to produce this causal structure. And in this particular example, this 1/2 is there. I have too many 1/2s floating around. The n there is a result of that repeated factor. What about this anti-causal sequence? Again, this is where people get a little bit confused because our tables are typically produced or generated for causal sequences. But we now need to introduce this sign negation between the time domain expression and its z transform. When you see anti-causal or a region of convergence that corresponds to anti-causal, alarm bells need to go off, and you need to go, okay, I need to be a little bit more careful with how I interpret the tabular data in these z-transform tables. So now let's say we're given capital X of z is 4z times the quantity z minus 4 over z squared minus 7z plus 10. This denominator can be factored. And now we can write that, or find the partial fraction expansion for capital X of z over z. That's now a1 bar over z minus 2 plus a2 bar over z minus 5. And I'm barring those just to remind myself that I'm dealing with an anti-causal structure. You can find a1 bar and a2 bar exactly like we have before. And here you can use the cover-up method because they are distinct. But now when we want to go into the time domain, look at what has occurred. Here we found an 8/3, but we now know, since this is a non-causal or an anti-causal structure, there has to be a sign reversal between the frequency domain and the time domain. The frequency domain, now with this being 8/3, that's a positive coefficient, so we need to change the sign when we go into the time domain, and that's why we have this minus 8/3 here. We have a sign reversal because we're dealing now with non-causal waveforms. Likewise, the A2 bar was 4/3. We have a sign reversal. If we wanted the exact sequence, if somebody just said, oh, give me the structure, well, that negative sign could be incorporated into the coefficient, and you might see it written then for structure. Oh, that's just some amount of 2 to the n, u to the minus n minus 1, and it's plus some amount of 5 to the n. The mode is 2 to the n and 5 to the n. You have two modes, and they are non-causal terms. In general, here's sort of a summary. What do you know here? Well, this now says causal, as does that. This is the region of convergence, and this now says, oh, I have a causal. Now you can directly read those from the table. But if somebody now gives you a non-causal sequence, or they give you a region of convergence that indicates a non-causal sequence, then you have to have this sign reversal between the Z-transform and its time sequence. Because, as we said before, this looks exactly like that. What's different between the two are your region of convergences. One is unbounded beyond the pole. One is a disk inside the pole location. The disk is the non-causal. Now, if you had a repeated pole factor, that now gives rise to this n, and you might go back to an earlier lecture where we were looking at what happens if you now said something. Well, let me finish this up. Where does that n come from? If you remember your Laplace days, you might have looked at the Laplace of t. Or when we just said, oh, what's the Laplace of 1? And we knew we were dealing with causal waveforms. What was the Laplace of a unit step? That was 1 over s. If we integrated that unit step, we would have a t, and that would now give us a repeated pole at the origin. So now this is just a constant times t. Well, that's what this, if you now sampled that t, now you have this scaling factor of n, which is similar to the scaling factor of t in the time domain when you're going into the discrete setting. What can you tell me about this? That now, this region of convergence says that this is a causal sequence, and there's no sign reversal between the transform pairs. This region of convergence says, oh, I have a disk now for my region of convergence interior to my smallest magnitude pole. I have a repeated pole factor. Remember now it's a little bit different. There's now this r in the numerator but you can then adjust for that as we will illustrate. Suppose that you now solved for or found an a sub 2 doing a partial fraction expansion, and that was your y of z, and now somebody says, oh, there's your y of z, capital Y of z, and here's your region of convergence. What does that now tell you? Well, this now says that you're dealing with a causal sequence. And what is little y of n? What's that sequence? Recall the transform pair. The transform pair actually had an rz over z minus r quantity squared, giving rise to, so here we have a 1 and there's a 1. If somebody now made this a 6, this would be a 6. What I'm trying to indicate is that if somebody actually determined that this numerator was equal to 10, we don't just have a 10 right here. We have to incorporate that r into the 10. So, if somebody now said, oh, I have a sub 2z over z minus r squared, well, now you know that you need to make sure that your transform looks like what it does in the table, which is rz over z minus r quantity squared. And if somebody's now found the a sub 2, well, you now need to find the b sub 2 by equating b sub 2r with a sub 2. If b sub 2r is equal to a sub 2, then you know that b sub 2 is a sub 2 over r, and that b sub 2 can now go in and be the weight or the coefficient on this time sequence. It's causal, and it has this n, capital R to the n structure. I think that's enough. Hopefully that will get you more comfortable with the second attempt on the Unit 3 quiz.